Morning. Hope everybody's doing well. We're going to talk a little bit more about gravity today. Hopefully the stream cooperates. We'll see how it goes. It seems to be doing okay now, knock on wood. Um, Before we jump into that, a couple announcements. Uh, there's been some chatter in the chat just now about the quiz, so I will send out an email reminder as well, but I wanted to take a moment and remind everybody to do the two components of our Newton's Law quiz. So there's the piece that's in the homework system that's very similar to what we did the first time around. Some multiple choice questions, sort of a lot of conceptual questions. And then there's also a piece on Blackboard, which is just a free response problem. You have lots of time to do that, but be sure to get it in before the deadline because it does need to be due, or you need to get it in today, this evening, by this evening. And for both of those, uh, there's not really a good way to administer them compared to how we would do in class, but make sure that it's your own work and that you're not, don't ask the internet, in other words, for solutions to the problems, because I think that is only going to backfire in the long term, because once we get back to class, you're not going to have that option, right? So, okay. Anyway, I will send out an announcement about that. Yeah, so in a comment about a stupid mistake on the homework system, that kind of stuff is going to happen. And it's the soulless, unforgiving nature of that can really be just devastating. But I'm trying to structure that in such a way that you kind of have lots of room. So if there's the occasional mistake like that and you're kicking yourself, don't sweat it. It doesn't mean anything, right? It's an inherent limitation of these electronic systems. So if you find that said, if you find like a problem with the system, if there's something that's like, wait, this question is wrong or something, let me know and we'll get it straightened out to everybody's benefit. Okay. Um, are there any other questions actually about that, about the quiz and stuff? Yeah, sure. Sometimes the language can be an issue too. It very much. I've noticed this too. Sometimes the way that they word questions is not ideal, and it can make it more difficult to understand what they actually want you to do. Like I said, don't let that get in your head or get you down. It's just a yeah. The online portion is timed. hmm But with regards to that timing, so with conversations with students, I think it kind of messes with you, or it can for some students for sure. It gets in your head, and you get like, what if the time, that it's timed, and I know that I've had that experience before. So the way that it is now is it's more questions. And that sounds counterintuitive, but it should be like more easier questions in that it gives you a chance to get kind of more on the board. And that way my hope is that you feel less pressured about any particular question. Yeah, I don't know what the best answer is, but maybe that would be a way to go about it. Um, in terms of, yeah, just Dylan, your comment about sort of a mix of conceptual questions and problems. I think maybe that's a good compromise. We'll see how this having the component on Blackboard treats people. Um, but that might be a reasonable compromise. So that's why we're trying it out. We'll try it out. If it works well, we can proceed from there. However it shakes out, I want you to feel like any problems with it are gonna err in your favor, right? We're gonna structure it in such a way that it's good for the students, because it's not fair to like pound you with quizzes or assessments or something when we can't, when it's like this untested way of doing it and stuff. So whatever we converge on, it's going to be to your benefit. Yeah, so I'm not going to turn off the timer in the assessment, because let's see. Huh, yeah. So, okay, let me see a couple comments regarding the. So, Carolina mentions the dynamic study modules. So these are it's basically like a conceptual list of questions, and it will sort of respond to what you how you answer, and give you some other questions in response to that. That can be something. Those are available to you in the system, so you can do those on your own. You can use those as a way to study, which can be useful. Um, so with regards to let's see a comment from Luke. The first quiz felt like a lot was not covered in the lecture. Hmm, that was not my perception. Although I would mention that some of that was we practiced sort of in lab. We did a lot of projectile motion problems in the computer. So I would encourage you to think of assessments as also, lab stuff is going to be relevant for that. But I will take that into account. I'm going to try and structure it so it feels like everything is connected to what we've been doing. I don't want to surprise you with something that you don't feel prepared for. So I will think about that and take that into consideration. Let's see. Cedric mentions that the timer is supposed to run in the background. Oh, there's an option you can hide it. So you can hide the timer so it's not like staring you in the face the whole time. That's a good idea. I'd also I noticed that you can, as you go through the questions, if you go to the upper left-hand corner, you can see the table of contents, so you can see the list of questions, and you can see if the one, checked off the ones that you've done. So that way you can go through the whole quiz, you can answer what you know, you could refer back to the table of contents and see what you have to do yet, and give you a lot of, way as a way to stay organized. I also noticed that in the first quiz, most people spent less time than you were allotted. So I think that it's sort of you have enough time, but if it messes with your head, it can definitely get you kind of messed up. So yeah, like I said, I appreciate your patience with all this. I think there is no ideal way of doing it. So we're gonna try some things. We'll stick with what's best, and however it shakes out, it's gonna be. I hope you feel like also that it's to your benefit. We're gonna do things that work well for you. So, but yeah, all right. I think that's good. If folks have further questions on quiz and or administration of stuff like that, uh, contact me via email or Teams or whatever, and we can talk about it. Yeah. So okay, back to gravity. So we're going to talk about a couple topics today. For those of you uh, who had our virtual lab yesterday, some of this will be connect a little bit, and for those that haven't, it will be sort of foreshadowing that, as well as giving you what you need to do the gravity homework. So there's basically two topics that we're going to get into. One is summing forces of gravity, which is kind of a nice. We'll look at one problem that kind of connects stuff that you already know how to do with um, this new ingredient, which is the force of gravity. And then the other thing that we'll look at is basically satellites and orbits, which is, I think it's a pretty neat and fun topic. So I'm excited to talk to you about that. And it connects with lab, it connects with the homework. Um, it's sort of the analytical side, the algebra side of what we did in lab. So, but before we do that, we're going to talk about sort of I'll call it, it's a little bit of a drier topic. It's maybe not as fun or interesting as orbits, but it is something that you want to know how to do. And that is basically summing forces. So let me talk to you about that by way of a example problem here. Make this bigger. So This is basically, it's superposition. It's summing gravitational forces, and let's see. So this is 6.3. We're getting into, yeah, this problem would be basically in 6.3, and then the orbits and stuff that we're going to going forward, that's basically section 6.4. So yeah, if you haven't already done so, definitely check out the text, chapter 6. Okay, so let me read you this question and kind of pitch it to you. Four masses are arranged as shown in the figure. Determine the x and y components of the gravitational force on the mass at the origin. Express your answer in terms of the variables m, x, y, and big G, and write the force in vector notation I hat, j hat. So first off, this problem is a little weird in that we don't normally think of arranging masses like this, because you think of masses as, and looking at the gravitational force, because the gravitational force is so weak that in practice, if you were to do something like this on sort of human-sized scales of distances and masses, you wouldn't really detect anything. It would be a tiny, tiny force. But it is really useful because it kind of foreshadows what you will do in 2021 with regards to electric forces, because the electric force is the exact same kind of math. It is a inverse square law as well. So we're going to work through this problem. So why we're looking at this is it's a good, it allows us to revisit vectors. That is definitely a subject that we want to be strong on as you go forward. And then also, it sort of foreshadows the electric force, which you'll get next quarter. Okay? Okay, so what we need to do is we need to find the force on M at the origin. So what this would look like is there is going to be a force of gravity between, let me try and draw this better. There's going to be a force of gravity between this 4m and the mass at the origin. And we could call that, for example, let's call it SF, let's call it 4m on 1. The subscripts that I'm giving you, these, you don't have to do it this way. This is just a suggestion. And I would point to the fact that, just in general, subscripts can help you keep track. You've probably already noticed with problems where you have, for example, multiple masses, putting a subscript can help you sort through, like, well, which mass is which? Does this mass cancel? Etc. Stuff like that. So I would recommend adding, using subscripts to keep track. I don't care what exactly how you do it, but it's a good problem-solving strategy. So we have that force. We're also going to have this force along the axis, the x-axis, due to 2m. And then we're also going to have, remember, the force of gravity points along a line that connects the masses. So there will be one that's along this line. That's the force of 3m on 1. And really what we're looking for is we're looking for those all added together. So we're doing a vector addition problem where we have these three components. And let me put this in another color if I can manage. So the net force is, it's going to be those added together. And that's what we're after. The net force on mass 1. Okay. Switch back to black. So, well, how do we go about this? Let's start by stating, we're going to be nice and organized. We'll look at the force contributions from each. Let's start with the force of the 4m on 1. So what is that going to be? Well, you know, based on what we've already talked about, this goes like big G m. So in this case, it'll be our 4m. And sorry, times the mass at the origin, which is m, divided by the distance. Let me just distinguish here. Let's call this x naught and y naught, just to keep straight the fact that those are actual distances. You know, like this is y naught, this is x naught, as opposed to y and x, which are the axes, the labels of the axes. So the r in this case would be y naught squared. And the direction that this is pointing in our ij notation, this is along the y-axis. It's pointing up. So this would be j hat. Okay. Force 2m on 1 is going to be very similar. G. Now instead of 4m, we have 2m. M. Now instead of y naught, the distance in this case is going to be x naught. And the direction in this case is in the I hat direction. It's along the x-axis. Okay. Now, the force of the the mass of 3m on 1 is where it gets a little more interesting. We're going to have big G 3m times m. Now, in this case, we need to know what the distance is. So, drawing this separately here. If we think about just this triangle, the hypotenuse of the triangle, you can use the Pythagorean theorem to figure out how large that r would be. And you know that that would be the square root of x squared plus y squared. So for us, since this is an inverse square law, what we would have on the bottom would be the square of that square root. So in other words, we would have x naught squared plus y naught squared. Now, that's fine, although that's just the magnitude. So this is the magnitude. It's at an angle, so it's a little more complicated. We need to figure out what the x and y pieces of that would be. And probably the easiest way to do this is to think of this as our angle theta. So how are you guys doing? Do you have any questions so far? Doing okay? Okay, so to get the I hat piece, the x piece, if we're thinking about it in terms of an angle theta, it gets to be, it's a little more familiar. We would want the magnitude of this force times cosine theta. Gah. Now, yeah, so you could do this different ways. One way would be, this is a good suggestion. We could use tangent theta to find what theta is. Because you know that tangent, And then if you have theta, you could plug it in. Another way to go about this, which I think we're so accustomed to working in terms of theta that we get, that's kind of the way we want to go. The other way that we can do this is we can directly define cosine theta and sine theta based on the picture. So cosine theta, recall that's going to be your adjacent over the hypotenuse by definition. So we could put in this whole thing as cosine theta. And similarly for the y piece, this would be the magnitude times sine theta. Well, what's sine theta? Sine theta is our opposite over the hypotenuse. We already determined what the hypotenuse is based on the Pythagorean theorem. Whoops, not x naught, y naught. So that's what we're going to do, because that way we don't have to go through the intermediate step of calculating the angle and then calculating the sine of the angle. So let me break it out. The y chunk, or sorry, the x chunk of this, the I hat piece, would be g 3m times m. Let me try and be a little more neat. Times x naught squared plus y naught squared times cosine theta. Well, cosine, can put cosine theta in terms of x naught and the hypotenuse. So in other words, this is times x naught over the square root of x naught squared plus y naught squared. And so this would be the chunk that's in the I hat direction. And we could simplify this a little bit. We can combine together the denominators. So this would be, oh man. Recognize that if we have this thing in parentheses to the power 1 times that same thing to the power of 1/2, that's the same thing as that to the power 3/2. So this is the x component of the force due to the three masses, the mass of 3m, on the particle of mass m at the origin. The y piece is going to be very similar. And I'll just write what it is. So 3m over x naught squared plus y naught squared, quantity to the power 3/2, times, instead of in this case, instead of an x naught, we would pick up a factor of y naught. So, and then just for sort of completeness, what did we want to do? Well, we were looking for the net force, right? On so what we need to do is we need to add these pieces together. Let me just, I don't want to rewrite all of that. So actually, I'll write it like this. These pieces, we need to add together, 1, 2, 3, 4. Two of them are just x pieces, and two of them are in the y direction. So I can write that for you, and we can factor out this factor of g times m because it's common to everything. So this will end up as g times m, actually m squared, sorry. Notice there's a factor of g, m, m, that's in all the terms. So I can factor that out. And then the different contributions. So from the 2m piece, we would have a factor of 2 over x naught squared. Then the contribution from 3m, sorry, in the x direction, we would have 3 x naught over and that's just the x chunk. And then the y contributions, we'd have our 4 y naught squared plus that's just the j hat piece. So that is the net force so it's kind of a lot of terms and stuff, but conceptually it's not that different from what we have done before. We are finding the force contributions in x and y and adding them together. It's different in that that force depends on the distance, how far away it is. It's a non-contact force as opposed to like a cord or multiple cords that are pulling in different directions or multiple pushing forces. So the result that we get out is more complicated, but it's the same, the same kind of approach. We find the x and y components and add them together. Are there any questions, or what questions do you have about this? Questions? So like I mentioned, it's not necessarily the most exciting kind of problem, but I think it is good. It gives us a chance to revisit vectors, which is a topic that you really want to have command of. Vector addition, etc. Good. Shall we proceed? Okay. Yeah, give me some feedback in the chat, and we can move forward here. And of course, if you have lingering questions about what we just talked about, you can post under the video in the comments. You can contact me. We'll want to make sure that everybody's okay. So this is kind of an interesting subject, and I hope that the lab this week will also be will kind of help with this. So in lab, we basically looked at this in a numerical way. We had a simulation, a program that took some initial conditions and mathematically, numerically determined via integration how satellites and stuff would behave. What we're going to talk about now is basically how do you look at some of that behavior analytically? How can you use math, algebra, expressions to determine quantities of interest in these kinds of problems? And this is all basically how do you solve problems? So this is, of course, extremely relevant to what you need to do for the homework for this chapter. And it's basically all based on one relationship. So the types of problems that we're thinking about are, you have like a satellite or something that's whizzing around. Um, the satellite, recall, it's going to have some velocity. There is going to be a force that's directed towards the center. Now, instead of a tension force, this will be the force of gravity that we know how to calculate. And then, of course, since this is in an orbit, where it's a rotating situation, there's a centripetal acceleration, AR. And centripetal acceleration, we talked about in the last chapter. You need some force to allow, to keep the object turning. So in this case, it's gravity. So when we go to sum the forces, do Newton's second law in the radial direction, we know that we talked about how that would be mv squared over r. So the force in this situation is the force of gravity, g. Let's call this the Earth. Let's call the orbit will have some radius r. So it's going to be the mass of the Earth. The satellite, we'll say it has some mass ms. So the mass of the Earth times the mass of the satellite over r squared. This is going to equal the mass of the satellite times v squared over r. This is basically the springboard, the starting point for many questions and problems that you can solve. And students have asked me before, like, what formulas should I know for a given chapter or something like this. Much of what's in this chapter you can come up with if you just start here. That's how I approach a lot of these problems. So it's an example of where I think sometimes you kind of have to strike a balance between how many things you want to remember or how many things you want to, formulas that you want to keep track of. This is a good place to start. It can get you a lot of different things. Okay, so we now have an explicit connection between masses, the radii of the orbit, the velocity of the object that's. So let me show you an example of this, and that is something called a geosynchronous satellite. So I should have a animation of it here. So this is a type of orbit. Let's see. Yes. So R refers to the center of the Earth to the satellite. Yep. So a geosynchronous orbit is like this. It's where you orbit at such a height and velocity that you complete one orbit per day. And you can use this to basically park your satellite over some location on the Earth, provided that it's close to the equator, and watch that location. So I'm sure that if you want to know what's happening there all the time, this would be a very valuable orbit, is my impression of why, I don't know for what purposes exactly, but if you needed to be in contact with some location on the Earth, this is how you can do it. And so this animation hopefully helps you kind of have that vision of what the orbit looks like. The Earth is rotating, but the satellite is rotating at the same frequency. Let's pull our whiteboard back up here. So, of course, an animation is going to be better than the picture that I'll try and draw, but you get the but you'll get the idea. So, there was a question about where R is. R is centered at the center of the Earth. Like we had talked about, we can treat these distributions of mass as if they were points with all the mass at the center. So a lot of times it's easier to work with R and then figure out things like height after the fact. So that's what we're going to do. So basically we have, the Earth is rotating, and our satellite is out here somewhere. And it's it's going around as well. And actually, I should put this more like at the equator. So in this situation, the satellite remains above the same location. And I'll add near the equator. And we can ask questions like, well, or sort of the natural question that comes out of this is, how high does the satellite need to be? I.e., we want to find R. Where, like we mentioned, R, and then we can relate R to the height above the Earth once we find it. So you'll notice a lot of questions that if they ask you how high, that's how high above the Earth's surface versus R. We can translate back and forth between those. So, okay. So let's start from the basics here. If we sum the forces in R, we are going to have GMM over R squared. That R is what we're looking for. That's going to equal the mass of the satellite times its velocity over R. And notice some of this stuff is going to we can cancel it. So we're left with a relationship that GM of the Earth over R is going to equal V squared. Okay. So yeah, no, 0 is the center of the Earth in terms of R. So let me draw this a different way. Suppose, like from the top, this is R, this is H, this is the radius of the Earth. So one thing that we need to straighten out before we can solve this question is V. We know the velocity in a sense in that we know that the satellite is going to make one rotation per day. But we need to put that in terms of a velocity, i.e. meters per second. So the way we can think about this is we have the Earth, we have the satellite that's going around. Really, we're talking about the speed too. although you'll notice the text and everything uses v, but we don't care about the direction so much as how fast it's going. And that will be, it's the distance over the time. Well, for one revolution, this would go one circumference of that orbit, right? So this would be 2 pi r. And that's going to happen in one day. And I'm going to denote that by the capital letter T for period. That's the convention for talking about a time for one cycle. So this relationship, though, that v is 2 pi r over t, or equivalently, you could say t is 2 pi r over v. This is another piece of information that you'll find is super useful for solving problems. So I would file that away. So what we're going to do is we're going to put that in here. Okay. And then recognize we're trying to find r. So we need to solve this basically for r. So let's do that. Let's multiply by a factor of the period squared. We can multiply this factor of r over, divide by this factor of 2 pi quantity squared. Okay. And then, of course, if we wanted this, we want r, we have to take a cubed root of this whole situation. Okay. And then let's evaluate this. So big G, 6.67 times 10 to the minus 11. The mass of the Earth is 5.98 times 10 to the 24. These numbers, like the mass of the Earth, are definitely things that I put them on a Post-it, keep it handy. It's a number that you'll find occurs again and again when you're doing these kinds of problems. And then the period, so that time, we want to put that in seconds. So what would that be? Well, that would be 1 day in seconds would be 24 hours times 60 minutes times 60 seconds. So that would tell us the number of seconds in 1 day. And recall that whole thing is squared. We're going to divide that by our factor of 2 pi squared. Take a cubed root. And then once we evaluate that, we find that r is 4.2 times 10 to the 7 meters. So that's r. If we want to talk about the height, notice from over here, r is going to be the radius of the Earth plus the height. So if we want just the height, we can take r minus the radius of the Earth, yeah? So the height will be this 4.2 times 10 to the 7 minus the radius of the Earth. The radius of the Earth, 6.4 times 10 to the 6. And so we get something like 3.6 times 10 to the 7. Meters. And that's the height. Um, and so notice, like compared to the radius of the Earth, this is something, it's like 6 times the radius of the Earth. So if we're trying to be careful about our picture, this distance should be about 6 times the radius of the Earth. And this gives us a sense of where the satellite is relative to the surface of the Earth. Um, so this 6.4 times 10 to the 6, this is the radius of the Earth. So I think it's often most convenient to work in terms of r, and then you can do this like we did just now and subtract off the radius of the Earth at the end to find the height. You can see alternatively what you could do is you could have this in the question already. You could have your algebra set up so that you did GMM over r Earth plus height. But then you have to track this term, you have to track this thing around, and it'll be, cubed and squared and stuff like that. So I think it's easier to just add it in at the end. Or not add it in, but you know what I'm saying, like account for it at the end. Um, questions? Questions? So, man, I can't write on this thing. The other thing that we can do is we can find, that's sort of a natural question to ask, is we can find the speed of the satellite, which is kind of interesting. The speed is given by 2 pi r over the period, which is, just what we talked about up here. So now we know what r is. So this is 2 pi times 4.2 times 10 to the 7 in this case, divided by our period in seconds. So you can see, 4.2 times 10 to the 7 is a pretty darn big number. When you crunch the numbers, you get 3,070 meters per second. That's, 3 kilometers per second. More than 3 kilometers per second, which is fast, right? It's hard to think about that in terms of, what we're accustomed to in sort of daily life. We could figure out, why don't we put that in terms of miles per hour? So if we multiply it, let me multiply that situation quick here. So that's like 6 million miles per hour. Fast. Um, okay, so, and I mean, that gets at the fact that if you're in your, you can only achieve something like that in outer space where there's no air and there's no friction. Because if you, and you've probably seen anecdotes about, if you had like a particle or something that's whipping around can cause a huge amount of damage to something in space if it hits it because it can be going so fast when there's no friction, there's no air to slow it down. So um, it's part of what's fun about these kinds of thinking about these kinds of questions is just that it's so different from our experience, and yet it's also definitely real because we have satellites whipping around the Earth, um, and we've been to the moon. Like these things are real, but it's just a whole different whole different kind of league of speeds and um, energy and kinetic energy and stuff that we'll talk about later. But and it's pretty neat. So that speed is all coming from gravity. That's a very interesting question. I would think about it this way. That speed is what's required to have that orbit. And think of it as gravity is providing the centripetal acceleration. And in order to have that orbit size, you have to have that speed. Those things are linked together by our starting point. The fact that GM. So it's not that that's being caused by gravity per se. It's the gravity is allowing for the orbit, and that's the speed that would be required. Let me see, 6.7 thousand miles per hour. I could be wrong. Yeah, I might have done my math wrong. Check here. Yeah, I don't know. My math might be off. Oh, wait a second. Yeah, or wait. Oh, yeah, yeah. No, I have a factor of 1,000. I'm off by a factor of 1,000. You're right. You're right. Because this is kilometers and I multiplied by the meters per second. Good catch. So this would be more like 7,000 miles per hour. Yeah, good point. 7 million seems really like a real big number. So thanks for checking my math. I am going to make mistakes like that when I'm doing stuff on the fly. So it's good for us to have a back and forth. We can check. And so I appreciate you guys, paying attention and checking my work. Um, but yeah, your question, Luke, back to your question. That's an excellent question. That's a deep question. I feel like my answer was kind of long-winded, so I don't know if that's super satisfying, but uh, I really appreciate that question. That's an excellent way. It's sort of a door to thinking about a lot of different things. So let me check my math once more. Are there other questions while I'm doing that? Yeah, so technically this is more like 6.8 times 10 to the 3. Other questions? Yeah, so yeah, I think that yeah, so the 3000 Carolina should be 3 because it's in kilometers. Yeah, you can so I think you can see kind of from this question, and there are a lot of different questions that you could ask. Um, yeah, so suppose you had some velocity, right? You could figure out. So yeah, that's a good question, Luke. I'll just add here, so sort of generally, you can see there are a lot of different kinds of questions you could ask. So, for example, if you're given a velocity, you could figure out, and that's kind of what we were doing. We were given a period. We knew for this orbit that it had to orbit once a day, but you could, for example, be given a velocity in meters per second or some other unit, and come up with what would be the orbital radius for that. You could be given a radius uh, and need to determine what the velocity would be for that radius. You could be given the characteristics of the orbit and have to find the mass of the planet or whatever that's providing that. There's a lot of different directions. I think you'll find once you start messing with the homework, um, is combinations of this kind of stuff. Um, so I don't want to go too. I want to. I'm trying to be better about our time. I don't want to. I know. I will do. Does anybody have class at noon, or is that an open time? I mean, I don't want to step on it in either case. I'm just curious. So I'm gonna kind of wrap things up, but so we're not going to talk about any more problems, but we'll talk about some more tomorrow. Other questions? So, and then I would add, something that thinking about lab, kind of what's cool with that is you can take these situations and you can ask the question, well, what happens if you just put in some, you pick a radius and you pick a velocity, you can see if it will, what kind of orbit it will get you. Depending, so you can model any system that you want. So for those that had lab already, you kind of got a flavor for that. You could do things like mess with the parameters and see if you have an orbit or if it just flies off into space or if it crashes into the Earth. And for those that haven't, you'll see that on Friday. So in terms of office hours, yeah, I have office hours. Just make sure to contact me beforehand. So I'll be free at 12:30 until whenever, but just let me know to meet you. You know that if that makes sense. The quiz is just chapter 4. There's no friction or circular motion. It's just Newton's laws. Yeah, quiz is just chapter 4. I'll send out an announcement about that too, or a reminder. Okay. Other questions? Well, yeah, if you want to, yeah, not a problem. If you want to meet for office hours or anything, ping me on Teams or on email, and we can meet up. Otherwise, I'm going to try and be better about time and end our